Hello, everybody. All right. Welcome to the spontaneous stream because I needed to go through this paper and I figured it would be more fun going through the paper with you. 1 second. I just need to do something. Hold on. No, yeah, no. No. Okay. Well, let's see what happens. Yeah, see that. Why is that popping up? What is this? What is this? What is this? That is not what we want. Okay, there we go. All right. What am I doing? Right. So, welcome in to a very random stream. Today, we need to go over this paper. Or I need to go over this paper, so I thought I would take you guys with me as I go over said papier. Any questions? Any problems? Concerns? All right. So this is a paper that was published in 2018. All right. Now this is talking about, right, high frequency surface wave radars have been shown to provide blah 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 blah. Can receive ionospheric echoes. But the important part in this paper, the radar cross section of ionosphere for HFSWR is estimated. All right, so we need to get this and we need to distort it a little because I believe we'll verify this, but I believe this is a out and back, right? So a backscatter radar. So it hits the ionospheric, the ionospheric plasma, and then parts of it gets reflected back. We're interested in, based on the data that I have, looking at trying to understand the ionosphere, right? We're looking for bistatic, right? So we're looking at this case. Goes up, bounces, comes down. But I would like to put that in terms of the RCS, right? Easy peasy, lemmy squeezy. Right. So HF-SWR uses sea surface diffraction characterization of vertically polarized wave, which can achieve long-range detection due to low attenuation over a highly conductive sea surface. Ideally, a perfectly conductive plane consisting of sea surface is infinite in coverage area, thus making transmitted wave entirely travel along the sea. That is the surface wave part of it. However, considering the actual antenna pattern characteristics, poor ground, and array error, partial energy is radiated into the sky and reflected off the ionosphere. Finally, the echoes arrived at the receiver in various paths, interfering with target detection severely as ionospheric clutter. So in their case, right, they're looking over surface of the Earth and they want this path, right? And so this is clutter. But we actually want to know this because we're looking at the science of the ionosphere itself. So that's what we're looking at. Okay. Ideally, a perfectly conductive plane consisting of sea surface. Okay, right. We said that. All right. The ionospheric clutter primarily restricted the detection performance of HFSWR. Therefore, in order to analyze and simulate the effect of ionosphere on the radar system, it is necessary to establish the estimation of the radar cross section, or RCS, of the ionosphere for HF SWAR. Right? So again, under these conditions, right, this is the path I care about. But some of my energy is going to go kind of this way, and some of it's going to go down and bounce up, right? And so from here, it hits the ionosphere, and then some of it goes back this direction, and some goes back this direction. So we're getting reflections from the ionospheric layer that they don't want, right? So they want to know, how do you characterize the cross section, the radar cross section, which is telling you what percentage of the energy that impacts it comes back, is happening in the ionosphere, right? Now we want to use that information because we want to know what's happening in the ionosphere, but we'll get back to that. The ionospheric clutter primarily restricts the detection performance, therefore, in order to blah, 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 right, we said that. It is conceived that the ionospheric clutter mainly occur from coherent scattering between electromagnetic waves and irregularities caused by plasma instabilities. The theory of ionospheric coherent scattering was initially produced by Booker, which demonstrates that the major contribution to the scattered field is given by a spatial spectrum component of energy density fluctuations whose period along the propagation direction scale size satisfies the Bragg scatter conditions, producing constructive interference at the reflection point. Right. So so what's he saying? So what he's saying is that what's happening is, that's not what I want to do. Right. So what's happening is, you're getting these little plasma irregularities, right? They're changing your index of refraction. What that's doing is scale sky satisfies the Bragg scatter condition. So what's the Bragg scatter condition? Good question. Let's see if we can figure this out. Bragg scatter condition. Okay. Bragg scattering. Okay. Bragg scattering explains the effect of reflection of electromagnetic waves on periodic structures whose distances are on the range of a wavelength. This phenomenon was investigated. Okay. So in certain wavelengths, regular periodic structures with a constant distance in between allow coherent superposition of reflections from the faces, thus constructive and destructive interference. Destructive interferences here are quite meaningless. Constructive interference can strongly reinforce echo signals in the direction of the radar receiver. This constructive interference occurs in a certain ratio between the transmitted wavelength and the distance of the reflective subsurface. Okay. Distance of the reflection. Okay. With variable transmission frequency can thus be the distance between the radio structures. The effect is used to measure, for example, the height of waves. Sure. Distance of the reflective subsurfaces. So is that the distance between the periodic? Okay. So what he's saying is that the energy is hitting these different objects, right? That are within D equals lambda over 2 cos theta, where theta is this angle, right? Yeah. And this is the distance d. So if d is in this at this instance, so that if the distance d is here, you'll get coherent scattering back, right? That's the Bragg scattering. Produce constructive interference at the refraction point, right? According to collective scatter theory, the backscattered ionospheric echoes come from a large number of ionospheric irregularities within the effective scatter volume, which is formed by the interaction of the antenna beam with the ionosphere. The coherent scattering theory between HF SWAR that has been used in HF SWAR to obtain several ionospheric parameters. In this study, we developed the RCS of the ionosphere in detail and intensively analyze the effect of each variable on RCS for HF SWAR, which could help quantify the impact. Okay, this paper firstly generalized the radar entry credit for distributed. Okay, sure. So, but okay, so they're saying that it's under the Bragg scattering condition. We'll see if that holds as it goes on. Okay. Most classical radar equations for monostatic radar in general, forget HF SWAR, are defined as blur, right? So my power received is equal to power transmitter times the gain of the transmitter, gain of the receiver, lambda squared over 4 pi cubed r to the fourth ls times sigma, right? So ls is system loss, r is range to target. Right. The ionospheric scatters should be modeled as distributed scattering from a three-dimensional volume rather than a single point scatter. Because of the distributed characteristics and gain of the antenna varies with theta and phi, GT and GR should be replaced by GT of theta phi and GR of theta phi, respectively. That accounts for the effective antenna power pattern on the power intensity radiated in a particular direction, theta phi. All right, so what are they talking about? So if my antenna beam looks kind of like this, right? You'll have theta in one direction and phi in the other. I'm gonna erase this. This doesn't look right. Right. So yeah. So if I'm looking at the beam, right, or I'm looking from the radar antenna, right. So this is the radar antenna that I'm looking at. I believe theta is down this way and phi is this way, right? Which one is theta phi? No, wait. Theta is down from Z, right? So if here's my plane, here's Z, then here's X, and here's Y, right? This should be theta, and this should be phi, right? For a vector going out in that direction. The point being that I'm characterizing each point from the antenna to the ionosphere as a specific theta and phi. And so the antenna pattern is not universal around here, so I'm going to characterize my antenna pattern by the theta and phi. Sure. Okay. Consider the scattering from an incremental volume, dV, located at a range. At range, angle coordinates are theta phi. The incremental RCS of a volume element d sigma square meters, the incremental backscatter from dv can be expressed as this. Okay. So, excuse me. This is the backscatter, right? So if I go and look at where is it? Where are you? Where are you? No. Dog. Python. Oh. Where's my freaking step radar? Oh, here we go. There we go. Oh, God, dog, freaking chewing all of my books. Anyway, all right. So, let's see. There should be another angular dependency, right? Let me see if this has RCS in it. Radar cross section. Here we go. 1920, 22 through 24. Okay, so this is transmitter azimuths, radiation patterns. In general, dependency of the transmitter and receiver patterns should be taken into account for the range equation. Therefore, the dependency of the radiation pattern on the angle considered, the equation of detectable RCS can be reformulated into, okay, well, that is the pattern radiated depending on the azimuth angle and elevation angle theta. Whereas GR phi theta is the receiver pattern depending on azimuth and elevation angles towards the target receiver position. Okay. So the difference is going to be that this theta and phi and this theta and phi are now going to be different, right, for our case. So what's going to happen is you're going to look like this. So here's the ionosphere cube. Right? This is my cube dV, right? And so each part of this has an, two angles to it from the transmitter, right? So my transmitter goes up and it's going to hit some part of this here, right? And some part of that's going to reflect this way. Some part of this is going to reflect this way, right? Now here is my receiver. Right? So now this receiver is going to be seeing a little bit from this point and a little bit from this point, et cetera, et cetera. So essentially what happens is this and this are going to be independent, right? Hey, Tencel! Hey, it's good to seeing you. I hope things are going well. I just realized you cannot see what I was hacking at. There we go. Okay, so today what we're doing is we are looking at it's not doing too bad. I've got a lot going on my plate right now, but otherwise it's going pretty good. We had a Had a nice collab with people yesterday that my stream just freaking died on. My wife and I were both trying to stream it, and I think the game we were playing was like really poorly set up netcode, so it was very resource intensive, and so both of our streams were just like chugging along. But anyway, that was fun. We had a good time. Otherwise, dog is being his usual pain in the butt self. And I'm trying to understand some radar cross section, ionospheric radar cross section stuff. How are you doing? What's new on your end? Dude, real world always comes first. Do not worry about it. It is all good. That's new a lot. Yeah. Well, hopefully mostly good stuff. It's been a busy few weeks for everyone, I think. It's been kind of nuts. See, that doesn't come up there. That's so weird. Oh yeah. Oh, that's right. That's right. I hope things have progressed well. I I'm very interested to hear how things are going. If you feel comfortable talking about it. If you don't, not a problem at all. Don't worry about it. I just hope things are going well for you. Oh, I was gonna do that, doesn't I? I'll close it out later. I need to buy out the rest of my Trevor Project donation thing. Oh yeah. Was this right after the last meetup you guys had? It is after. Okay. Visible on there? That's really not. Sorry, I'm just while you're typing stuff out, I'm just gonna try and fix something here. Just try to expand this way. There we go. Yeah, I mean, so I will tell you, communication, man, is the single most important thing. Like talking, communicating effectively is that's what makes a relationship actually exist. Let's see. There, I can move over a little bit more. It's still not good enough. Sorry, I'm trying to that improve. Two most important. Fair. You know, I'm gonna switch this back. I'd hope this would be more readable, but I think it's less, if anything. We're just gonna do this. You can go over there. There you go. It's a little better. So I don't think that those are distinct, right? I think that that is just another method of communicating, of expressing yourself, your interests, the things that are important to you. It's sorry, it's still jacked up. Come here, you. Um, I presume music, but would you care to elaborate? Do you play music, by the way? Yeah. So, the reason why I say that about music is a vehicle by which you can communicate, but the communication itself is important, and sometimes the communication needs to happen in a more direct way, more not more direct, but a less ambiguous way sometimes, right? And so music can be a form and an enhancement and a mechanism for communication, but it's not the only way, and sometimes in and of itself it's not sufficient to provide the types of communication that you might need. But it is certainly a method thereof and absolutely an important aspect. It's because that's part of showing the things that are important to you and seeing what's shared amongst the important things. That is awesome. Holy cow. How many of them overlapped? Although sometimes it's good if you have very different ones and like you kind of open each other up to different yeah, so how many of them are the same songs? But I was just thinking, you know, sometimes it's good to have different separate interests because you can share things that the other person maybe hasn't encountered. I am, however, I will say that hey, that's a good percentage, right? Because that shows that you guys have a lot of the same interests, but you also have range outside of it that you're like, oh, look at this one. Oh, look at this. Oh, I've never heard those guys before. That kind of thing. So that's really cool. Yeah, that is a great way to share things back and forth. That's awesome. I'm so happy. I was dreading a little bit when you came on. I was like, oh no, did something go wrong? And then when you start talking about, I'm like, and talking about music sharing, I'm like, oh, phew. Sounds like things are still going good, which is awesome. Oh, so exciting. Oh, that's so. Sorry, I get silly and enthusiastic about stupid things. Anyway, yeah. Oh, no worries. I love hearing this because I don't know. It just makes me happy hearing about that. Yeah. So what are we doing? I'm looking at stuff in the ionosphere, right? Which is, the plasma layer in the upper regions of the atmosphere, where the energy of the sun creates a plasma that reflects radio waves, right? So you can bounce radio waves off of it. And I don't remember which streams you were in where I was talking about these things, but I essentially trying to look at the radio waves that are being bounced off for a specific experiment set to try and understand what the conditions are like in the ionosphere, right? And so there's a bunch of different ways that you can try and do this. And one of the ways that I'm trying to analyze this is essentially in terms of what I'm calling like a loss field. So the way to think of it, if you're like looking down at a map, right? Say here's my transmitter. If I'm over here, I can expect a certain amount of loss. If I'm over here, right, I can have a different amount of loss. And then because there's weird stuff going on in the atmosphere, I might have an area where I have very low loss or very high loss. And then I might have something over here. And then I might have like another area that's a different amount of loss on my signal and all this kind of stuff, right? So my signal might be strong over here, but then weak over here, that kind of thing, right? And so what I'm trying to do is I'm trying to say, okay, well, I can kind of 2D heat map plot this loss field that I'm calling. So it's telling me how much of my signal that's coming from my transmitter is lost if I were to put a receiver here, or if I were to put a receiver here, or if I were to put a receiver over here, right? I would have different amount of loss from my signal that's going this way, this way, this way. This is a look down two-dimensional thing. Of course, it's actually bouncing off the ionosphere and coming down like this, right? That's what the signal's actually doing. And there's going to be some loss in this reflection. Cool, fine. So but people haven't really typically characterized things like this in this way. The closest thing that I found is what's called the radar cross-section, which goes something like this. If my radio wave is coming in like this, and it hits something here, some of it is going to reflect back, right? And so if I had a radar here, I can pick up this part that reflects off in this direction. Now, some of it's going to reflect in this direction, some's going to reflect in this direction, some's going to go this way, etc., right? But I can only see it wherever my antenna is to pick it up. So if I say how much of my energy that I sent out actually bounces back to me, I can call that a radar cross-section. Like I could say that's the equivalent of, it turns out the units come out to be a unit of area, right? So I could say it's, 1 square meter is the area of my radar cross-section. Now the actual area of the thing that I'm bouncing my radio waves off of can be bigger or smaller, right? This isn't the physical size. This is the equivalent size. If I perfectly reflected all the energy off 1 square meter, it would look like this, right? So depending on the shape of what it is I'm bouncing off of, right? Depending on the shape of this and depending on the frequency and a whole bunch of this other shenanigans, a certain amount of my energy is going to reflect back, right? Cool. So these guys are saying, okay, well, we can take that that setup or that understanding that's used in radar, and they're looking at a radar that does like Where'd it go? Did I erase it? Of course I erased it. Okay. So they're looking at a radar that goes like this. Here's my transmitter and receiver. So this is my radar. Here's the surface of the Earth. You can imagine this being water or something, right? And if I send out certain frequency signals, you're actually going to get two paths, right? Some of them are going to hug the dielectric difference here, right? They're going to refract around the curvature of the Earth like this, and some are going to go and they're going to bounce like this. And in addition, I did say hug, yeah. So in other words, it's going to keep close to the Earth. I did say hug. So some of the energy, essentially what's happening is some of the energy is seeing the this boundary, which is like, this might be water. Say you're looking over the ocean, right? This might be water, and this is air, right? So there's this boundary layer here, and it'll go and kind of stick around close to that boundary level, right? And then if it hits something over here, it'll bounce back along this way. And so that's what their radars are looking for. But things are more complicated than that in reality. Of course, they always are. So what's happening? Not all of it gets the hug. Some of it gets the bounce. So some of my energy is going to go this way. Oops. It's going to go this way and then bounce up this way and then bounce back. And so, right? Some of my energy is going to go straight up, hit here, and then bounce back. Some of my energy is going to go off of here, bounce over here, and bounce back, right? So I'm going to have all of these different ways in which the energy that's able to reflect off of the top of the atmosphere is getting back to my radar, and they don't want this, right? Because all of this energy makes it confusing to understand what's over here. They're looking at stuff on the ground. So they're trying to say, okay, well, we can look at this as this radar cross-section. Well, I appreciate it, but always stay hydrated. You could be chugging with the other hand. You could be chugging water. I appreciate you. Right, to these guys, all of this stuff is nasty clutter and they don't like it. To us, this is exactly what we care about because we're trying to understand what's going on up here. We don't care about what's going on down here. So they're looking at, okay, if I take some cube of this atmosphere, right? And I say, well, how much bounces off from this? That's what they're kind of talking about with down here, right? So this is the typical radar equation. You see this all over the place. It's telling you how much of your power that you sent out from the radar you're getting back, right? So again, how a radar works is I send out a radio wave, I bounce it off of something, and I listen for what comes back to me, right? So how much power is that? Well, it's the transmitter power. Yeah. You come right back. We'll hang out here. No worries. I will try and fix. See if I can get this looking a little better. Oh, what did I want to do? I wanted to do something. What did I want to do? Okay. That's not very helpful, is it? Oh, hey, Mark's here. Hey, Mark. Hi, Mark. While Utensil Archer is gone, I did want to throw this out there. We do have a donation link for the Trevor Project. Here, I will put in. Let me let me do me a little donation. So I'm gonna donate. I don't know, $10. Okay. Ay. Okay, yeah, give me the code, blah, 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 send me the text, blah, 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 blah. Okay, 8. Okay, there we go. And we're gonna do that, and we're gonna do that, and ta-da! It worked. Oops, I didn't mean to close that. All right, so I just wanted to put that up there that we do have this Trevor donation project or Trevor project donation link available. Okay, hey Tencel. I was just saying we're doing a little donation thing to the Trevor project, which supports LGBT youth. Specifically provides suicide prevention services for it. So I just wanted to throw that out there that link is there. So feel free to tell people that they can, if they're interested in donating to that, either through this donation link or on their own. It's a good cause. It's a good charity that's worth supporting. So I just wanted to throw that out there. Anyway. Hi, Mark. I hope you are doing well. I don't know how much of the shenanigans you came in to see, but we're trying to do some radar cross section work here. Okay, right. So, long story short, what we're looking at is how much of the energy that actually hits this comes back, right? That's what they're looking at. Okie dokie. So you've probably seen a lot of it then. So that's what they're looking at. And we're trying to change what they're looking at into our setup, which is I have a transmitter here and I have a receiver here, right? So I'm bouncing up some my radio waves up into the atmosphere and I'm looking at the bounce, right? So it's a little bit different, but it's very similar. If you think about it, the only difference is I now have an angle between my transmit and receive paths, right? I now have this new angle, theta, whatever you want to call it, right? Actually, I'll call it something different because theta's here. I'll call this angle gamma, right? I have some angle gamma here that is between these two, whereas before my angle was 0, right? It was out and receive along the same path. There's no angle between the two. So, so now we're going to look at where the radar cross section, how this works in here. This is the standard radar equation. So this is telling you how much power you're going to get back if you transmit out a certain amount of power, right? You have a certain amount of gain from your transmitter and receiving antennas, right? So this affects, is your antenna transmitting in all directions? Or is it taking that energy and is it focusing that energy down into a beam, right? And so you'll get these beams that look kind of like this, right? And so a parabolic dish antenna will look something like this, right? You'll have this main beam. This is where most of your energy is going in this beam here, right? No worries, Utensil. I hope you get some fun out of this, and thank you so much for coming in and telling your story. As it keeps going, I'm super excited. This is just really cool. And I hope you sleep well to some insane math as my brains leak out my ears because I'm trying to understand this. But yes, again, thank you so much for coming in, for sharing. I'm so excited to listen to your stories about this. I know I shouldn't spend all my time listening, talking about you, but it's exciting. Anyway, have a wonderful sleep whenever you kind of crash out. But until then, let's keep going. So, right. So we have our transmit and receiver gain. That's our antenna, right? We have our wavelength of our radio waves that we're sending out. That's just the, you're sending out a wave that looks like this and it has a certain wavelength, and that's determining your, how it's going to interact with things. 4 pi cubed is coming from, oh, that's so kind. I'm glad that my streams can help provide some entertainment. Someone else you might enjoy, who also has very kind of calm demeanor and doesn't talk about boring math stuff. Let's see. Shoot. How do I do this? Nope. Shout out. Hold on. 1 second. Sorry. I want to get her actual channel name. Here we go. You may enjoy this person's streams. Toasty Morsel. She does some wonderful streams. She was one of the people I was playing games with yesterday. She actually has it on YouTube as well. If she's another one you might also enjoy. Just kind of a good person that does good streams. So definitely worth checking them out. Yeah. Anyway, sorry about that. Thank you so much for listening to my streams. I hope my streams provide you with entertainment and a good time, and maybe learning something. Yeah. So I appreciate having you come around. So feel free anytime, no pressure, but it's always great having you in. Anyway, where's I going? Right. So the 4 pi is from the fact that my waves are actually propagating in 3 dimensions, right? What's actually going on, you can think of it like this. It's propagating like a sphere, right? So it's going like, you can imagine this as the surface of a sphere. So at a certain point of time, I'm going to have a certain radius here, right? Then later point of time, it's going to propagate. Again, it's propagating out in all directions. So it's like a bigger sphere. So taking into account how things are distributing over time means I have to divide by the 4 pi cubed. I've got r to the 4th because this is where it's going to be a little different. In this case, it's got r to the 4th because I'm going out and then bouncing back, right? So the out and back means I have r squared twice. So again, the surface area of the cube is, or of the surface area of the sphere is 4/3 pi r squared, right? No, 4 pi r cubed. I'm sorry. No, I'm an idiot. 4 pi r squared, right? right? And that's 4/3 pi r cubed, right? Yes, 4 pi r squared. Yeah, she has good streams. She has good streams. And she also does a really good job with her YouTube channel. Yeah, absolutely. Anyway, long story short, two of the R's here are from going out, and 2 of the R's are from coming back, right? So this is actually going to be 2 different values for R's. And LS are the losses, right? So you have losses from absorption. You have losses from the fact that I really wish that my dog hadn't chewed on my pen. I could show this so much better if my dog hadn't chewed on my pen. So I've sent, here's my little radar antenna. I've sent radio waves out like this. They bounced off of something. They're coming back like this. How much of that power am I actually capturing? I'm only capturing this much of it, right? I'm not capturing all of it. I'm capturing this much of it. Right, so I have the propagation loss. I have the antenna gain loss. I've got the loss of going through the atmosphere itself, right? There's some losses involved there from just propagating through the material. Essentially, you heat things up in the atmosphere, and that takes energy away from your signal. So this is, anytime you do any sort of radar course, you'll see this formula, and this right here is the radar cross section itself, right? So PR is the received power, PT is a transmitted power, G is the transmitter antenna gain, R is the receiver antenna gain, sigma is the RCS, pi is the radar wavelength, R is the range to target, and LS is the system loss, overall system loss, right? Now, when I'm dealing with the ionosphere, it's a little bit different, because now I'm looking at kind of a volumetric thing. It's not just a single point scatterer, right? It's not just seeing this single point and bouncing back. It's actually different parts are going to be radiating from different points in the volume in different directions. So, okay. Distributed scatter from a 3-dimensional volume rather than a single point scatter. Because the distributed characteristics and the gain of the antenna varies with theta and phi, remember I said my antenna beam looks kind of like this? Well, I have the most gain here, and I have less gain here and here, right? Most of my gain, so most of the energy is concentrated in this small area. So that means I have less energy to bounce off of what's in the way over here than I do over here, right? I have more energy over here than I have over here to bounce off. So that's why the path matters, right? Varies with theta and phi, where, by the way, in general, I believe theta is the azimuth angle. Hold on one second. Let me verify this. I believe theta. So when you're doing all right, we're gonna go on a little bit of a divergence here. If I want to characterize a 3-dimensional space, there are a lot of different ways I can do it, right? I can talk about Z, X, and Y, right? So then I could say that this point is point X naught y naught z naught, right? Is this point right here, for example, right? And so that would be kind of the, oops, that's really terrible. It's hard to do this with a mouse. I can't wait till my new freaking pen arrives. Anyway, right, so that's point XYZ, or I can do something like this. Let's change this to something a little bit. Let's do a rainbow. Let's do a little rainbow, right? I could look down like this and say, all right, we've got, you know, this is kind of at this point here, right? And I've got an angle here, theta, and I've got an angle here, phi, and I can say I know I'm some distance r away from it, so I can talk in terms of r theta phi, and that'll also get me that same point, right? R naught, theta naught, phi naught. And I could go back and forth between these two, right? There are conversions back and forth between them. This is just a spherical coordinate look. And for some things, this makes more sense. One makes more sense than the other, right? If I'm looking from a you know, a radar beam point of view, and I've got this beam that might be like this, right? And it's actually a cone kind of thing. It's an ellipse sort of thing, right? If I make a line straight up in this direction, I could talk about theta being one way and phi being the other way, right? They're just two angles, and I could use that to describe it. So I'm just using angles instead of XYZ points because it makes more sense in this case to use angles because all this stuff is working with that kind of math. So that's why things are talking about theta and phi. So in this case, right, I'm looking at this entire volume, which is some volume here, right? It's no longer just a single point. It's a whole box over here that I'm saying is filled, and I'm looking at this whole box, and I'm trying to figure out what's going on at this point versus this point versus this point, how much of my energy is going to bounce back to me from these different points. So I have to know what my angles are, right? My theta and phi angles are, because those are going to tell me where I'm actually pointed to. That's how I know where my arrow is pointing to at any one given point in time, right? So I'm going to characterize it in terms of theta and phi, which is my look angle, right? It's a certain amount from the vertical, it's a certain amount down, and it's a certain amount, you know, in the kind of XY plane. You could think of it like that, right? I have a certain angle in that way. So you can think of this as like a compass. Here's another way to think of it. Phi is kind of like your compass directions. So if I'm looking straight down now, right, I could have north, east, right? I can have an angle here that's giving me a compass direction, and this is my phi angle. And now look how far down I'm looking from vertical is my theta angle, right? So one's looking around horizontally in a different direction. The other is looking down vertically from vertical. And so each point in my cube is some specific theta and phi. And so I can integrate over my entire volume, right? Integrate over all my cube to add up all the different components from all the different theta and phis. And I have the different R values for each of these points, right? And each of them is going to scatter a certain amount of energy back towards me. Here's where it gets different. There's a couple places where this is different. In our case, we no longer have R to the fourth. We have RT squared, right? Which is the distance from our transmitter to our point in the sky that's the energy is bouncing off of. And then we have R squared, which is the distance from this point in the sky to where my receiver is. And these aren't necessarily, in fact, probably aren't going to be the same. So that's different, right? And I'm going to have two different thetas and phis, one for my transmitter. So I'll have theta T and I'll have phi T, and one for my receiver, right? So this is the angle looking up in this direction. And then I'm going to have another set of angles looking in this direction, right? So I'll have theta R and TR, right? So these are different because one's from the transmitter and one's to the receiver, right? Okay. Now here's what's interesting. My sigma is going to also have to be broken apart, right? Because if I'm hitting some surface, some rough surface, right? And my radio wave comes here and scatters. How's it going to scatter? Well, some of it's going to scatter in this direction back, right? That's the back scatter. Some of it's going to go in this direction. Some's going to go in this direction. And how much of it goes in the different directions is going to depend on the shape and the material that it hits at, right? So, what this means is now I'm looking at I have two angles. I've got this, and if I care over here about what's coming at this angle, right? Certain parts of this are going to reflect certain amounts in this direction versus other directions, right? So now, tentatively speaking, I'm going to also have sigma is now also going to be a function of RT, RR. No, we don't need to do that, right? We can reduce those two. It only needs to be one of them because it'll be the right. We can just say RT, right? Because it's the same point, and then it's going to be a function of theta T, theta R, BT, BR, right? Because it's going to matter both what your transmitter angle is and what your receiver angle is. So this is all going to get a lot more complicated, right? So the total power is obtained by integrating over that. That's fine. So we're integrating over our little dV volume here, or over our volume here to get our total power that's bounced off from all the points. We're adding together the power that's bounced off from each point in my volume. Okay, so equation 3, the volume integration V is all of three-dimensional space. However, only scatters within a single resolution cell volume dV contribute significantly to the radar. Therefore, a more appropriate form of generalized radar range equation can be given by this. Oh, jeez. Right. So that's another added complexity, right? Because we are not looking at a radar range cell. So how can I describe this? All right. Here's how I'm going to describe this. I have a radar, right? And my radar is going to send out a pulse. It's going to wait. It's going to, oh, God dang it. Really? That was not what I wanted. So my radar is going to send out a pulse. It's going to wait for a while to listen for reflections. That's going to send out another pulse. Right, so this is time. Wow. Awesome. That was a very straight line. Right, this is time. So it's going to send out a pulse. Then it's going to wait for a while. Then it's going to send out another pulse. Cool. Now, range resolution cell. Or is the range resolution cell the width of the pulse? It might not be the... Hold on. There's two different things, actually. Range resolution cell. I might be describing the wrong thing. Range resolution. Here is our log pulses. Higher average power. Okay. Resolution formula. Hold on one sec. Let me see if it's. I think it is. Okay. Okay. Resolution ability to distinguish two or more targets with the same bearing but different ranges. Excuse me. With the transmitted pulse. Okay. Pulse width is a primary factor for range resolution. Well, the design radar for maximum efficiency. Okay. Sure. So I was describing the wrong thing. I was talking about unambiguous range. Here's. I wasn't wrong, but I was talking about the wrong thing. Okay, I have a radar. My radar is going to send out an energy pulse like this, right? In time. Again, this is time increasing this way. Now, if I have this pulse is going to move at the speed of light, right? It's going to move along at the speed of light. So that means in the time it takes for the pulse to hit something here, right? So in the time it takes for this pulse to go across this delta t, right, is going to tell you what your overall range resolution is. Because if I have two different things I'm bouncing it off of, right? Targets in radar nomenclature. So I have two different targets, right? I have target A and I have target B. This is A and this is B. If I'm listening over here and I'm the radar, I can't really tell the difference between what's target A and what's target B because they're both in the same radar pulse, right? So I can't really tell which is which. They're within the same range bin, if you will, or range resolution cell. So I can't really tell them apart. If B, however, is all the way over here, then A, I'll have a gap in my time between the pulse A sends back and then the pulse B sends back. So I can distinguish between pulse A and pulse B, right? So that is the integration period that it's talking about with the resolution cell DV. Right? Because this, in any time that you're talking about a radar system time equals distance, the distance equals times, right? You can go back and forth between the two pretty easily. Because they're all modified by this. They're connected by the speed of light, right? Your radar wave, your radio wave is propagating at the speed of light, so you can just transform back and forth between the two pretty easily. So in general, time is distance, distance is time in radar speak. So when they say dV, what they mean is my area that I'm looking at and the volume that corresponds to my pulse width, right? Or the distance that corresponds to my pulse width for my third dimension. So this gives me a volume, right? And this is my dV. Okay. However, that is not the same for what we are dealing with, right? Because we don't have this narrow pulse, do we? We have a time integrated receive pulse. And it's what, like 30 seconds? I mean, that would be the entire ionosphere. Thinking. So instead, my delta V is going to look a little different, right? My delta V is going to look like the entire ionosphere up to the point where I have high enough plasma frequency that I'm going to get just a full reflection, right? And then that's going to be this volume here, right? Interesting, right? Because I'm theoretically getting scattering from everywhere along this pathway. So it's going to be that entire pathway that's going to be scattering. Okay. Okay. Here, eta is reflectivity, so just a thought. But okay, we define eta as RCS per cubic meter or volume reflectivity, then d sigma equals eta dV, right? So my infinitesimal amount of reflection is going to equal my RCS per cubic meter times my cubic meters, obviously. Here, eta is reflectivity of effective scatter volume, ESV, which is formulated by the intersection of the radar beam with the ionosphere. For the antenna having an elliptical beam with an azimuth and elevation beam with theta 3 phi 3, sure, the resolution cell delta V R theta phi can be approximately expressed as this. Where delta R is the range resolution. Okay, so I mean, we could still theoretically use this, but in our case, right, the delta R is going to be the entire column, the entire ionosphere column. Okay. Where delta R is the range resolution. Sure. Thus, the RCS of the volume can be obtained by this. Okay. Considering the attenuation of electromagnetic wave propagation in the atmosphere, and using approximation 6, we can produce equation 3. We can reduce equation 3 to the range equation for ionospheric scatterers, which is, let's see, what did they do? What's different? Okay, so if you notice, they just replaced sigma with this thing here, and then they separated the losses into LS and LP. I'm not sure what the difference is between those. Okay. According to the Bragg scatter conditions for monostatic backscatter, radius equals gamma radar over 2. I'm sorry, lambda, the frequency of my my irregularities has to be lambda over 2, where lambda irregularity is the scale size of the ionospheric regularities, which means the scale size of irregularities between 5 and 50 meters, as observed by H.F. Swar. For the magnetic plasma in the ionospheric region, irregularities at these scale sizes are highly anisotropic and aligned with the geomagnetic field, right? So what else is happening here? Just to add this complexity to it, right? We have our magnetic field lines cutting across here, and all of this stuff that's going on in the ionosphere are charged particles. So what do charged particles do in a magnetic field? They start circling around the magnetic field lines, which means what goes in this direction is very different than what goes in this direction, right? They're going to see very different things because you have, it looks different in different directions. So that's another set of angles we're going to have to care about. Man, this explains why my method is a lot simpler. But anyway, I need to understand this because I'm going to be writing this up in these terms and saying, all right, look, my method makes more sense. Or my method is easier to utilize. Okay. The reflectivity of ESV depends on direction, electron density, and scale size of the irregularities, which can be expressed as eta is a function of k, which is the radar wave vector in the medium. So that is your wave vector. Vd is the drift velocity of the irregularities. So those irregularities are not in the same place every time they're moving. Phi is the flow angle, the angle between the radar wave vector and the drift velocity. So if my little irregularities here, the wave's coming this way, maybe this is heading off in this direction, right? Now I have this angular difference between which way this is going and which way the radar is. Okay. This is K, by the way, is the direction of the signal. Just for, let's say, okay, i.e. the angle to alpha is the aspect angle, i.e. the complement of the angle between K and B. So again, now my magnetic field lines are doing like this, right? So now I have this angle here, which is alpha. This is B. Here's my geomagnetic field line. And here's my signal vector coming up in this direction. All right. L is the scale length of the irregularities, which we talked about before. FEI is the electron and neutral collision frequency. Delta NE is the average level of electron density fluctuations. and E is the electron density of irregularities, assuming that the magnitude of the electron density fluctuations has linearly it has a linear relationship with the electron density, which can also be consistent with experimental results. For convenience of discussion, equation 10 can be reduced to this. So eta is proportionate to my electron density squared times the exponential of negative 2k squared L parallel squared alpha squared L perpendicular squared. Well, L parallel and perpendicular are the scale size of the irregularities along and across the external magnetic fields. B. Equation 10 is based on the assumption that L parallel is much bigger than L perpendicular, and KL parallel is much, much bigger than 1, so that eta appears peak when alpha equals 0, namely when K is perpendicular to B, which means that the major contribution on the backscatter field is only a small region of the ESV. So when my signal is going perpendicular to my B field is when I get the most backscatter. In summary, our analysis reveals that the backscatter ionospheric cluster of HF-SWAR should be dominated by the specific ionospheric region in which the wave vector is near perpendicular to the electromagnetic field in a simplified fashion. Okay. But now we are no longer under the assumption that this is going up and down to the same place. Instead, it's going this way. So what does that mean? Well, I guess it doesn't matter. It just means that your alpha is not going to be 0. No, wait, that alpha is not that. Alpha is not that at all. Your alpha is never going to be 0, which is true. But it's also going to matter the direction compared to B. Right? Because anisotropic. So this is going to be different than this. Interesting. Huh. We might have to grab a... So I have a bistatic radar book, but I might have to look at... Excuse me. So I might have to pull some more stuff from this bistatic radar book. Which I wish I had a digital version of to go through. Okay, simulations and analysis. Okay, we don't care about their simulations. We only care about modifying eta. Right? That's all we care about is modifying eta. Effective scatter volume. So we're going to have to change our effective scatter volume, which is formed by the intersection rate of beam with the atmosphere. For the antennas, elliptical beam aspect. Okay. Oh, this could be interesting. Woof. Oh, this is going to be a lot. Because we have to modify our ESV. So we have to modify My ability to think is starting to taper off. I may have to come back to this tomorrow. Are you still going? Jeez. All right. So what do we have to do? 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 For convenience of discussion, equation can be reduced to what are 9 and 10? Fluctuation level of the asymmetrical regulars from backscatter measurements and reflective index effect on the scatter volume location Dopplers. Ooh, I want that. 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 Marenko PV and Rice. Refractive index effects on the scatter volume. Okay, let's see. This should be enough. Okay. Refractive index effects on the scatter volume, location, and Doppler velocity of ionospheric HF backscatter echoes. Knowing HF backscatter characteristics. Okay, so that's where they got that. Effective scattering cross section irregularities depends on their intensity, shape, and orientation. Okay. Right, so that's the backscattering piece. Checkers with some flight models. Dependence. So this is probably another good one to have. So I'm going to go ahead and print this out over here. Not you. You. Spam phone calls. Yum. Okay, so we should be printing to here. Oh yeah. Oh yeah. Okay. Right. So we've got this printed out. So we can go through this one as well. I'm gonna have to come back to this tomorrow, I think. My brain is just so I hope some of that made some sense to you. Yeah, my brain is a little bit fried about now. I think if it's all right with you, I think I would like to play a video game. My tea's gone. Actually, I need to see if dog needs a walk first, so I guess I'll just stop the stream. Thank you so much for hanging out as I go through this. I know this was a little random and a little wacky. But I think this is good. It's good. I know kind of where I need to go with this. It's just gonna take gonna take some time, unfortunately. Yes. So anyway, thanks for hanging out, Mark. I appreciate it. I hope that you had at least a little bit of fun listening to me ramble along as we do this. So have a wonderful night. Thank you so much again for hanging out, and as I just spam my way through stupid shit. I appreciate you. I really do. So have a good night, and I'll see you next time.